So, very good evening to everyone, and welcome to the NPTEL's fourth live interactive session on the course Mechanical Behavior of Materials. So, in this course, in this live interactive session, we will be going to solve some samples problem based on your weekly content, which will in turn will help you to solve your weekly assignments. Okay. So in this session, first we will recapitulate what are the things that we have seen in week 4, then followed by the concept related question, and if the time permits, we will try to discuss the week 3 assignment, week 3 and week 4 assignment. Okay. So let's begin. So week 4, we started with the concept of flow stress. Okay. Flow stress. So, what is flow stress? So, flow stress, it is an instantaneous value of stress which is required to keep deforming the material. Also, it is locus of yield point. So, instantaneous value of stress to keep deforming the material. So, and it is locus of yield point. Why is it so? We will see. Okay. So, okay, let's say this is our stress strain curve. Okay, so this is our yield strength. Okay, so if we load the material above its yield strength and we unload it, so it will follow this path. Okay, so let's say this is yield strength 1. So now if we again load it, so it will follow that green path. Okay, so the second path, and suppose at this position if we unload it, so it will follow this orange path. Okay, when we again load it, it will follow the same path. Okay, so yield strength 2, and while we unload it, it will follow the blue path. This yield strength 3. So what we have seen here is that the yield strength 3 is greater than yield strength 2 is greater than yield strength of 1. So what is happening here? The strength is increasing with the deformation. So strength usually increases with the deformation. Okay, and this, if we take the locus of all these points, so we will get a flow stress curve. So that is why it is the locus of yield point. So to model flow stress, one equation is used, and that equation is known as power law. And power law is given by the equation sigma T is equal to K epsilon T to the power N, where sigma T is nothing but a flow stress or flow stress, where K is nothing but our strength coefficient. epsilon T is our true strain, and N is our strain hardening exponent. Okay. So this we have seen about the flow strain. Then after that, we have seen the rate of strain hardening. So what is the rate of strain hardening? It is the rate of change of true strain as a function of true strain in a material undergoing a plastic deformation. Okay. So let me write down the definition. Rate of change of true stress as a function of true strain in a material undergoing plastic deformation. That is d sigma by d epsilon. So this is our rate of strain hardening. Okay. So if you find out equation, that is d sigma upon d epsilon, and if we take a derivative of power law, we will get something like this. And if we simplify it, we will get N sigma upon epsilon. So what are the things we are observing here? Means if the material is to be deformed at the faster, the more stress needs to be applied. So this means if it is to be deformed faster, more stress need to be applied. More stress need to be applied. So after that, we have seen the effect of microstructure on strain hardening. Let's say this is my same material. That is, let's say this is solution annealed. Let's say this is my overaged, and let's say this is my underage material, and this is the graph for peak aged. So this is for the same material, but different microstructure. So from this graph, what we came to know, that the rate of strain hardening is very sensitive to the microstructure. That is the rate of strain hardening is very sensitive to the microstructure. Okay. So after that, we have seen the different variations of power law. Variation of power law. So let's say so this is my sigma epsilon. So first variation that we have seen, that sigma is equal to y. So it will directly show the plastic deformation, no elastic deformation. So this is for perfectly plastic material. Okay. The second variation that we have shown, that it will start something like this. Okay, and the power law is given by y plus a epsilon. Similarly, the third variation that we have seen just now, that is sigma is equal to k epsilon to the power n. Okay. If suppose some strain hardening has already done or pre-straining, then it will start from somewhere here. Okay, E naught, and this equation will be modified as epsilon plus E naught to the power n. Okay, and also we have seen one more variation like this, and the equation will be sigma naught 1 minus exponential minus a epsilon. Okay, so these are the variation of power law we have seen. So the power law is usually not applied for very low strain values. Okay, so then we have came to know that power law behavior is usually not applied for very low strain values, that is epsilon less than 0.4. Okay, so after this we have seen some limitation of the power law. So what are the limitations of power law? The first limitation is it is not so reliable for low strain. Okay, so not so reliable for low strain. The second limitation that we have seen, that it is not suitable to predict the yield strength of the material, as we predict the yield strength of the material at epsilon equal to 0.02%. So it is not suitable to predict yield strength of the material. So And the third limitation is that if the material is already work hardened, then equation need to be modified. So material is already work hardened, equations need to be modified. So let's say I am work hardening the material by amount of strain E naught. So my new equation will come to be K epsilon plus E naught to the power En. Okay. So this is all about the power law. So after that, we have seen the concept of yield criterion. So we need to know, like, at what state of stress, at what point the material will yield. So this will give us the idea to design the material or to design our applications. So let's first see the definition of yield stress. So in yield stress, the material transits from is elastic to plastic regime. Material transits from elastic to plastic regime. Okay, one more thing. Then we have seen that in general the state of stress is not uniaxial. Okay, so it is subjected to multi-axial stress. So deformation is usually not a uniaxial stress condition. Okay, so then we have seen, like, one material is there and we have applied a stress of 200 MPa, okay, unidirectional load, and its yield strength is suppose 180 MPa. So what will happen? This material will yield. Okay. Then also we have seen the one condition that when the specimen is subjected to biaxial loading. Okay, let's say this is 220 MPa, and on the y-axis it is subjected to 50 MPa. So whether this material will yield or not. So let's find out. So let me draw the Mohr circle. So if it is uniaxial, okay, so uniaxial, biaxial, okay. So sorry. Let's say this is our biaxial, okay. So if I draw a Mohr circle for uniaxial, I will get something like this. Okay, and if I draw the Mohr circle for biaxial, so I will get something like this. So what we can conclude, that the size of the circle will determine the yielding will happen or not, but not the actual value. So size of Mohr circle will determine yielding, not the actual values. So after this, we have seen that if such situation arises, so how we can overcome. So then we need to define a yield in such a way that it should include the all state of stress. So, such situations, we need to define yielding in such a way that it should include overall stress state. Okay. So it should include the overall stress state. So what are the stresses are acting? The normal stresses in XYZ direction and the shear stresses. So let's see its function of sigma x comma sigma z. That is the normal stresses, and it is also a function of shear stresses. And let's say this some constant c prime. So if it exceeds the prime value of c prime, then yielding will happen. Otherwise, yielding will not take place. So if we talk in terms of principal stresses, so it is function of sigma 1, sigma 2, sigma 3 equal to constant. Let's say C. So then we have derived, then we have considered that yielding criteria for isotropic material, and we made some assumptions. So assumptions for isotropic So, as the materials is deformed due to the shear stresses, the magnitude of mean stresses should not influence the yielding. That was our first assumption. So, magnitude of mean stresses does not influence yielding. Okay. Now the second thing, that is no Boschinger effect. That is the yield strength in tension should be equivalent to the yield strength in compression. So that is yield strength in tension is equivalent to yield strength in compression, and there should be consistency of volume, that is mu should be 0.5. Volume. Okay. So this we have seen, and then we have seen as we are talking that the material deforms mainly due to the shear stresses. So then we have seen how the principal shear stresses can be expressed in terms of the principal stresses. So we have seen different conditions. Let me draw. So let's say this is subjected to sigma 1, sigma 2, and sigma 2. So this will be principal stresses plane, and the shear stresses, that is, and we have assumed that sigma 1 is greater than sigma 2 is greater than sigma 3. So tau 3 will be sigma 1 minus sigma 2 by. Okay. Now, suppose if it is subjected to loading in x and z direction, like sigma 1 and sigma 3. So this will be our tau 2, and it is equal to sigma 1 minus sigma 3 by 2. As you can see here, sigma 1 is greater than sigma 2 is greater than sigma 3. So this whole difference will be greater than all other differences. So this will be equal to our tau max. So that is the maximum shear stress. And similarly, we have seen, like, if the material is loaded like this, so we will have so this will be our shear plane, and the shear stress will be given by tau 1 is equal to sigma 2 minus sigma 3 by 2. So this was about the assumptions for isotropic material and how the principal shear stresses can be represented in the form of principal stresses. So after that, we have seen the stress tensor. Okay, stress tensor. So what is stress? It consists of 9 components. That is sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, and sigma zz. So if we see, okay, this stress tensor, what we can see that it consists of 2 stresses. One is the hydrostatic stress, or we can call it as mean stress, and second one is the deviatoric stress. So hydrostatic or mean stress. Okay, and second one is deviatory stress. Okay, so what are the features of hydrostatic stress? That is, it only involves pure tension and compression. And what is the second feature of hydrostatic force? It involves only elastic changes in the volume. So no, it doesn't consider the plastic deformation. Okay, it doesn't induce a plastic deformation. So involves only elastic changes in volume. On the other hand, deviatoric stresses, it represents the shear stresses. And also it is responsible for plastic deformation. So important for plastic deformation. So now we have seen how we can represent this derivative stresses. So first, we have seen like hydrostatic stress is nothing but the average of the mean of stresses. So it is nothing but our invariant I1 by 3, and it is responsible for elastic changes in the volume. So now we have seen the deviatic stress, how we can represent it. So let's say my sigma d is equal to sigma minus sigma m. So if I put that in this matrix, so what I will get, sigma xx minus sigma m. So let's write tau xy, tau xz, tau yx, sigma yy minus sigma m, tau yz. Here tau zx, tau zy, and sigma zz minus mean stress. Okay, if I put a value of mean stress in this, so what will I get? So I will get the matrix like this, like 2 sigma x minus sigma y minus sigma z divided by 3. So all these stresses will be the same. Only the change in these stresses will take place. So all this will be same. So only changes will happen in here. That is sigma y minus 2 sigma y minus sigma x minus sigma z by 3, and here 2 sigma z minus sigma x minus sigma y by 3. So this derivative stress we can get. Okay. So my sigma is made up of two stress condition, that is sigma m plus sigma ij, where sigma m is my hydrostatic component and sigma ij is deviatory component, and it composed only of shear stresses. So then after that we move towards the yield criterion. So there are some requirements, that is the yield criterion. So as the deformation is occur only by shear, so the yield criterion should be the function of only deviatoric stresses. Okay. So requirements for yield criterion. So since deviatoric stress, that is EF, I can represent shear stresses in the form of principal stresses. So sigma 2 minus sigma 3 and it is equal to some constant C. And the second thing, that as the deformation mainly depend on the shear, so the addition of the hydrostatic force should not affect the yield criterion. So should not depend on hydrostatic stress. And the third requirement that we have seen for yield criterion is that it should not depend on the choice of axis. Okay, so there should be must some invariant. That is, if we change the axis, the yield criterion should not change. So it should not depend on the choice of axis. That is, must be some function of invariance. Okay. So, and the final, that is the last requirement for the yield criterion, that is the size and position of Mohr circle should not determine the yielding. Okay. Should not determine yielding. Okay. So, based on this requirement and the assumption made for isotropic material, we have we discussed the first criterion, that is von Mises. So these are the all four requirements that satisfy the von Mises criterion. So if I take a second invariant, that is I2, and as it is consists of the deviatic stresses, so it is a good candidate for determining the yield criteria. So I can write J2, that is the von Mises 2 by 9 sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. That is, it is the second invariant of deviatory stress, good candidate for determining yield criteria. So if I write it in the form of some function a of sigma, and if I keep that 2 by 9 and equate it to and provide some constant, so equation will become sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square equal to constant. So when our F sigma reaches or exceeds the critical value of C, then only the material will yield. Okay. If F sigma is less than C, then our material will not yield. So F sigma, so let's see. When F sigma reaches or exceeds critical value C, then material starts to yield. Okay, so this is about the von Mises criterion. After von Mises, we have seen the which criterion? Tresca criteria. Okay, but before that, we have derived some relation between the yield strength and shear strength for von Mises, and it is y is equal to 3 scale. Yield strength is its root 3 times of shear strength, and we have plotted the area of yielding and no yielding. So it is, this is the ellipse. So this is my yield strength y, minus y and minus y. Let's say this is my sigma A, this is sigma B. So if our loading conditions are under this curve, okay. So this area, this green zone, so no yielding will take place. Here, no yielding. And if we go outside this curve, the yielding will take place. So here, yielding. And we have seen that from this also we can see that individual stresses, principal stresses can be higher than our yield strength, okay. But it doesn't mean that the material will yield. Individual principal stresses can be higher. So individual principal stresses can be higher than come on. Would you like to say something? Mohan, you're not audible. You can use the chat box if you want to say something. Okay. So, after that, we have seen the generalized form of 1 sigma y plus sigma x minus sigma y square plus 6 times our shear stresses. And it is equal to our 2 times of its yield strength square or 6 times of shear strength square. Okay, so this is the generalized form of 1 Mises criterion. Okay, so after that we have seen the next criteria, that is the Tresca, also known as maximum shear stress criterion.
Good evening, sir.
Yeah, good evening.
Sir, can you repeat especially the locus of the von Mises?
Yeah.
Yes, the curve, the yielding and the no yielding portion.
Okay.
How can I draw this curve? How to understand?
So how you can draw this curve? You want to understand it? Okay.
Yes, sir.
So when let's take that our equation, that is this equation, okay, that is sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square equal to, say, this equation. Here I am highlighting with the blue, okay.
Okay, sir.
Okay, so if we keep assume one stress in one direction is 0, that is, let's assume sigma 3 is 0. What will you get? Sigma 1 minus sigma 2 square plus sigma 2 square plus minus sigma 1 square equal to some constant c. Okay.
Yes, sir.
If you rearrange this equation, you will get the equation of the ellipse. Okay. If you need detailed explanation, so we can discuss it in the next session also as well. So I will give you in detail information how exactly you can derive this equation. Okay. So for time being,
okay, sir.
just remember that equation, and if we assume any stress to be zero, then we get a equation of the ellipse, and we can draw the ellipse like this. Okay, so I will explain it in more detail in the next session. Okay.
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 But sir, del A and the del B, and what is the measurement of the y? Just putting on the x-axis and the y-axis.
So that is not del, that is sigma. So that is sigma A and sigma B. So let's, instead of assuming
Sigma.
sigma 1, sigma 2, sigma 3, I am assuming sigma A, sigma B, and sigma C. Okay, and that y is nothing but the yield strength of the material. This is y. This y is yield strength of the material. Okay. So if I apply sigma A here, like greater than some value of yield strength, okay, let's say this point, and sigma B is less than the yield strength. So overall, our effective stress is coming in the range of, is under the curve. That means the effective stress is less than our yielding stress. So our the material will not yield. So have you gone through the concept of effective stress and strain? So that's why I have written that individual principal stresses can be higher than the yield strength. So individual stresses on the material can be higher, but the what will determine its yielding, it's the effective stress. Here in the very beginning I have discussed, like here in this equation, here you can see it is 220 and this is 50 megapascal. This 220 is greater than 180 megapascal, is it not? But if you see the Mohr circle, the stress, the shear stress that is coming, it is very less. So it is very less than the your yield strength of the material. So the material will not deform.
Sir, sorry to disturb, sir. Sir,
Yeah.
can you again repeat this portion, the yield criterion?
Okay, so what is the yield strength? It is the material that is it transfers from elastic to plastic regime. Okay.
Yes,
So
sir.
yeah. So for plastic regime, which stress is more important? It is your shear stress, is it not? Because for plastic regime,
Definitely.
yeah. So for this bimodal state of stress, if you draw the Mohr circle, so this green one is for the uniaxial. Okay, so this green one is for uniaxial. Okay, here you can see that the size of the Mohr circle is very much higher. Okay, and here when you draw, that is sigma 1 here, like say this is 50 and sigma 2 is here 220. So if you draw Mohr circle, it will be very less. So in the yield criterion, what we are saying that the size of the Mohr circle will determine the yielding of the actual values. So I am discussing that further. You will get clarified. Okay, after the Tresca. So when concept of effective stress will come, you will come to know why is it happening. Okay.
Okay, sir.
Yeah. So then we have discussed the Tresca criterion for maximum stress. So what are the assumptions in the Tresca? That is shear stress cause plastic deformation. This was the first assumption. And second is that yielding will occur only when the largest shear stress is reaches the critical value. Means there are several stresses applied on the material, but if the largest shear stress in the material reaches the critical value or reaches to the yield value of the material, then only the material will deform. So yielding will occur when largest shear stress reaches a critical value. Okay, so that means largest shear stress will be sigma 1 minus sigma 3. Okay, because what we are assuming is sigma 1 is greater than sigma 2 is greater than sigma 3. So the difference between sigma 1 and sigma 3 will be the largest. So this will be our largest shear stress. So it should be equal to yield strength or twice of shear strength. So then we have discussed the region of just a second. That is the stress for stress curve. We have discussed the region. So let's say this is my yield strength minus 1. Okay. So this is for my trace curve. Here in sigma 1 minus sigma 3 equal to C, let's assume the sigma 1 is sigma 3 is 0, then sigma 1 is equal to yield strength. So sigma 1 equal to yield strength. 1 point will get here. Then similarly, sigma, if we assume sigma 1 0, then sigma 3 we will get in the negative. So this is my one line. So if you assume conditions like sigma 1, sigma A is greater than 0 and greater than B, you will be able to draw this curve. So, and if you overlap, so with one mices, so we can see this. This is the one mices criterion. Okay. So after that, we have discussed one more criterion, that is Rankine or maximum stress criterion. Okay. So what does Rankine said? That yielding will occur when the maximum principal stress at any point reaches to the yielding strength of the material. So he consider only maximum stress. That is sigma 1, we can say, if we are talking about the principal stresses. So yielding will occur when maximum, sorry for the inconvenience. So yielding will occur when maximum any point reaches yield strength of material, that is sigma 1 equal to y. So this criteria is not defined for the yielding, it is defined for the failure of the material. Okay, because the application of hydrostatic stress leads to the change in yielding condition. So one of the requirement for yield criteria is that it should not change due to the application of hydrostatic stresses. So not for yielding, also application of hydrostatic stress leads to change in yielding condition. So this was about the Rankine maximum stress. Then we came across the concept of effective stress. Okay. So the material is not always subjected to our uniaxial condition. Okay, it can be subjected to biaxial or triaxial. Okay, but what we are defining yield strength is for uniaxial. So we need a stress such that which will consider the all state of stress and will give the effective stress, that of our uniaxial stress. So one mises effective stress sigma bar V is given by equation 1/2 sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square, and it is equal to yield strength. And then we have seen the trace ka, that is sigma bar T. It is nothing but a sigma 1 minus sigma 3. And then we have seen the effective strain. And effective strain is defined on the basis of incremental work done per unit volume is consistent. So, and for one mices, the effective strain is given by two by three epsilon 1 square plus epsilon 2 square plus epsilon 3 square. And for trace ka, it is maximum of all. Okay, so this was all about our the week recapitulation of last week content. So Swati Brata, Mr. Banerjee, so you were asking like why is it happening?
Yes, sir.
Okay, so just assume simply, okay, this is my material. Okay, so if I am pulling from here, this uniaxial, only one load is applied. Okay, so if the applied stress reaches the yield strength of the material, then only it will deform. Okay, because only in one direction I am pulling it. Is it not?
Yes, sir.
Okay. So now I am pulling with the same force. Okay, like suppose the strength of this pencil is 100 MPa and I am applying 120 MPa. Okay, so it should yield. Okay, but at the same time I am pulling it from this side. Okay, so what will do, this y component will produce some resistance into that of this pulling. Okay, are you getting my point?
Is Y component also leads to failure of the material?
Yeah, it depends. Depend on the value of y component, the material will yield or deform. So in questions, there are 2 or 3 questions is there. You can see like how the value of sigma x, sigma y affects the yielding. Okay, suppose if I am pulling from this side and pulling from this side, so this y, so what will happen? This will try to stretch material in this direction and it will try to compress material in this direction. Is it not?
Yeah, definitely, sir.
Yeah, and when I pull it from the y side, so it will try to stretch material in this direction and it will try to compress material in this direction.
Yes, sir.
Okay, so because of y component, you are trying to compress material in this direction. Okay, like in this direction, but at the same time you are applying stress in this direction. So what will happen? So there will be some resistance will generate. Okay, and it will not always means it will resist to the loading in that direction. So it is not always possible to have a yield when the biaxial stress is applied. So that's why we have made this yield criterion that it should consider all types of loading, like that is the normal loading in all directions and shear stress loading. So if the value of this sigma v means sigma bar v, that is the one mysis, it consider the loading in all direction, normal and shear. Okay, and it will give the effective stress. And this, if this effective stress is greater than the value of our yield strength, then only the material will deform. Are you getting my point?
Yes, sir. What is the last one? The effective stress is greater than the yield stress.
Yield strength, yeah, then only our material will deform. Mean effective stress means how much the effective stress. Suppose if in x direction I am applying 100 and in y direction I am applying 50. So and suppose the my material strength is 80 MPa. So 100 in x direction 100 is greater than 80. Okay. So what does is saying that the material should deform, but at the same time we are applying y. So the effective stress acting on the material is changing. So it can be less than 80 or it can be greater than 80. So depending on the values of x and y. So if the effective stress means the combined effect of the stresses applied in various direction is greater than the yield strength of the material, then only the material will deform.
Yeah, yes, sir. Got
Yeah.
it. And sir, is take an example that in the x-axis we applied 100 megapascal,
Yeah.
and in the y-axis 50. Then sir, we can easily put these two stress in the von Mises criterion,
Yeah.
having the value of the yield strength. And if it suppose greater than 80, then the yielding occurs.
Yeah. Yeah. That's what it is.
Okay. Yeah. Okay, sir. Got it, sir.
Yeah. So we have quickly recapitulated the last week content. Now we will move towards some concept related questions. Okay. So are you able to see the question? Please respond.
Yes, sir.
Yeah. Yeah. So the first question is the stress strain relation for a material is given as sigma equal to 150 plus 185 epsilon in megapascal. For this material in tension test, what percent uniform elongation can be expected? Determine the ultimate tensile strength of the material. Okay, so here let me draw the stress strain curve for you. So it is something like this. Is it not? It is following the equation sigma is equal to 150 plus 185 epsilon. Yeah. So, and what are they asking? The what percent of uniform elongation? So, what is uniform elongation? The elongation up to yield strength. So, let's say this is yield strength of the material. Ultimate tensile strength. So this is my uniform elongation. So what they are asking in a tension test, what percent of uniform elongation can be expected, and also they are asking us to determine the ultimate tensile strength of the material. So can you solve this question? It's very simple. Mr. Mohan Reddy, please try to solve this question, okay? And tell me answer if possible. Yeah, Mr. Mohan, you can talk now. Mohan, you can speak. So let's solve this question together. Okay, let's solve this together. So what they have given, sigma is equal to 150 plus 185 epsilon. Okay, now we know the true stress is given as sigma is equal to S 1 plus E, where S is engineering stress, and true strain is given by ln 1 plus E. Is it not? So let's put this value in this equation. So what we will get, S 1 plus E 150 plus 185 ln 1 plus E. Okay. Now for uniform elongation, okay. For uniform elongation, here the slope, that is slope of d sigma versus d epsilon, is how much? At UTS, slope is how much? Mr. Swati Prata, Mr. Mohan. Okay. So it's the maximum volume, the slope should be 0. Okay, so sorry, this is ds upon dE. So now, if I rearrange this equation, so what I will get? 150 plus 185 ln 1 plus epsilon divided by 1 plus E. So as I said, at UTS slope is 0, therefore ds by dE at UTS equal to 0. So if I take derivative of this S with respect to E, so I should get the equation something like this, like 0 is equal to 1 upon 1 plus E. Derivative of 150 is constant, is 0, plus 185 divided by 1 plus E, 1 by x, plus 150 plus 185 ln, sorry, 1 plus E into derivative of 1 upon 1 plus EU is how much? Minus 1 upon 1 plus EU whole square, and the denominator term, it will go this side and it will become 0. So only this much is the derivation of that equation. So now if we rearrange this equation, so what we will get, that is 185 equal to 150 ln 1 plus EU. So here you can see this term and this term is same. Okay, and if I take this equation this side and this term will get cancelled, only we are left with 185 equal to 150 plus ln 1 plus u into 185. Is it not? Mr. Swati Brata, Mr. Mohan?
Yes, sir. Yes.
Yeah. So now, if you solve, so 185u minus 150 divided by 185u is equal to ln 1 plus EU. Okay. Now solve this equation and tell me the value of EU. So it is 35u divided by 185u ln 1 plus EU. So if I take an antilog, so EU is how much? Mr. Swati Brata, Mr. Mohan Reddy. How much it is coming, Mr. Swati Brata?
1 minute, sir. Just.
So it should come around
0.20.
okay. So it is 0.20 means 20%. Okay, it's 2.208 na. So 20.8% is the uniform elongation. Now what? This is the answer to first term there, that is A part. Now B part, what they have asked, determine the UTS of this material. Now you have this equation and you know the value of EU. Put the value of EU in this equation and tell me the value of yes, that is ultimate tensile strength. So if we consider now at UTS, epsilon is how much? ln 1 plus EU. So epsilon comes out to be ln 1 plus 0.208. So epsilon comes out to be how much? 0.1892. Is it not?
Yes, sir.
Yeah. And sigma is how much? 150 plus 185 into epsilon 0.1892. So sigma is how much? 185 MPa. And if I put the value of EU in equation 1, so let's say what's so let's say this is equation 1. So I will get a value of S is how much? Value of S is how much? Huh? Mr. Swati Brata, Mr. Mohan. Okay. So if I put the value of EU is equal to 0.208, I will get yes somewhere around 153.11 MPa. So this is my for part B. Okay. So now moving toward the second question, that is, if the yield strength of the steel is 950 MPa, determine whether yielding will have occurred on the basis of both von Mises and Tresca criteria. The stress state is given by. So the stress state is given. Now you need to determine whether yielding will happen or not. So Swati Brata, you can try this question. Okay, it will answer your query.
Yes, sir.
Yeah. You know now, Swati Brata, how to approach to this question? You need to first find out the value of sigma 1, sigma 2 and sigma 3. Then in that sigma 1, sigma 2 and sigma 3, you need to keep it in the equation of effective stress. If it is less than yield strength, then material will not yield. If it is greater, then material will yield. So now the stress condition is given, means the stress state is given, and you can find out the sigma 1 and sigma 2 and sigma 3 using the equation sigma p cube minus I1 sigma p square minus I2 sigma p minus I3 equal to 0. And root of this equation will give you the values of sigma 1, sigma 2 and sigma 3. So let me write down the formulas first for all the cases. For one Mises, effective stress is given by 1/2 sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Okay. So I need to find out the values of sigma 1 and sigma 2. Now for Tresca also, effective stress is sigma 1 minus sigma 3. Okay. So now I need to find out the values of sigma 1, sigma 2 and sigma 3. So for that I will use equation sigma p cube minus I1 sigma p square minus I2 sigma p minus I3 equal to 0. So here I1, I2, I3 are the invariants. So I1 is nothing but sigma x plus sigma y plus sigma z. I2 is nothing but tau xy square plus tau yz square plus tau xz square minus sigma x sigma y minus sigma y sigma z minus sigma z sigma x, and I3 is sigma x into sigma y into sigma z plus 2 tau xy tau xz into tau yz minus sigma x tau yz square minus sigma y tau xz square minus sigma z tau xy square. So now I have given all the formulas. Now you can use these formulas and try to solve this problem. So Swati Brata, did you got the answer?
I'm doing, sir.
Okay. Now let's see. This is our sigma x tau xy tau xz tau yx sigma y tau yz tau zx tau yz and sigma z. Here you can see sigma x is 0. So in all these equations sigma x terms 0. So this will become 0 and this will also become 0. Here this will become 0 and This one also becomes 0. Okay. Now, this is of sigma x. Now, here you can see tau xy is also 0. So you can make tau xy term 0. So this one 0, and here this whole term is 0, and here tau xy. This one is also 0. Now tau yz is also 0, and tau zy is also 0. So tau yz, tau yz, tau yz, tau yz is 0, and tau zy is also 0. So I have marked all the values. Okay. Now put the remaining values. In I1, sigma y is how much? Minus 400, and plus sigma z is minus 800. So you will get I1 as minus 1200. Are you getting the same, Mr. Swativrata?
Yes, sir.
Okay. So did you got the values of sigma 1, sigma 2, and sigma 3?
No, so somehow I doing the wrong calculation.
Okay. Now here in tau xy is 0, tau yz, only tau xz square term is there. How much tau xz is 300? 300 square. Then we have minus sigma y into sigma z. So minus 400 into minus 800. So this comes out to be minus 23 into 10 to the power 4. Okay, this is your value of your I2. And here I3. So only this term is there. Minus sigma y tau xz square. So minus sigma y is minus 400. And tau xz is how much? 300 square. So it comes out to be 36 into 10 to the power 6. So now if I put values of I1, I2 and I3 in this equation, so this equation will become sigma p cube minus of minus 1200 sigma p square minus I2 is how much? 23 minus 23 into 10 to the power 4 sigma p minus 36 into 10 to the power 6 equal to 0. Now tell me the roots of this equation. Satibrata, please find out the roots for this equation. So sigma 1 comes out to be 100 MPa, sigma 2 comes out to be minus 400 MPa, and sigma 3 comes out to be minus 900 MPa. So now if I put this value of sigma 1 and sigma 2 and sigma 3.
Sir, can you please solve the equation?
So do you have the calculator? In the calculator you need to solve.
Yes.
Directly roots. So you can use the calculator. No issues.
Okay. But sir, in exam, can we use the calculator?
Yeah, but in exam you will get a simple equations, not like this difficult. Okay.
Okay.
Yeah. So.
And sir, one more question.
Yeah.
Sir, for the gate purpose,
yeah.
Can we have this equation?
Yeah, you
solve
can.
means is it possible to solve the equation via calculator?
In gate.
Yes,
No,
sir.
there you will not get like these types of question. You will just get a plane space condition out of this sigma 3 will be 0. Okay.
Okay, then it will be very easy.
It will be quadratic equation, then you can easily solve.
Yes, sir.
Yeah.
Okay, okay. Thank you,
Yeah.
sir.
Yeah. So sigma 1, sigma 2, and sigma 3. So these are the values. So now if I consider the one Mises criteria, one Mises. So sigma 1 Mises is 1 by root 2 sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. So if I solve this, if I put the values of the sigma 1 and sigma 2, so I will get something like this, that is 100. Sigma 2 is minus 400 and this is minus, so it will plus 400 square plus minus 400, and sigma 3 is minus 900, minus minus plus, so plus 900 square plus minus 900 minus 100 square, so 1 by root 2 500 square plus 500 square plus minus 1000 square. So how much it is coming?
866.025.
8
66.025.
866.02 MPa. Okay, now the yield strength, the given yield strength is how much? Here, the given yield strength is 950 MPa. Okay, so the sigma bar V is less than yield strength. So what will happen? The material will yield or not?
So no yielding occurs.
Okay, so yielding will not occur. So here, Swati Brata, you can see the individual stress component are less than the yield strength of the material. That is sigma z, tau, sigma y. You can see, but their overall effect is also less than your yield strength of the material. Is it not?
Yes, sir.
Yeah. If I change the value of suppose sigma z, if I increase, so what will happen? The material will yield because this value will change. Okay, and at one point, what will happen? This will reach the yield value of the material, and which will help to yield the material. Okay, so this is according to one Mises criteria. Now, what is the second criteria they are asking? The second criteria is which one? Tresca. In Tresca, what is the effective stress? Sigma 1 minus sigma 3. Is it not? So sigma 1 is how much? Is 100. And sigma 3 is how much? Minus 900. So what is its strength? Is 1000 megapascal. So now tell me, Swati Brata, whether yielding will happen or not?
Sir, definitely yielding occurs.
Definitely yielding occurs. Yeah. Now you got my point. Like
Yes, sir.
individual component can be less than the yield strength, but their effective effect can be more is greater than the
Yield stress.
yeah. So here sigma t bar is greater than yield strength. So yielding will occur. Okay. So now this is our next question.
Sir,
Yeah,
sir, from the von Mises criterion,
yeah,
if we not derive the sigma 1, sigma 2, or sigma 3,
yeah.
means by applying the simple equation sigma x minus sigma y the whole square plus means the
Yeah,
equation with shear
yeah,
stress.
you can calculate using that equation. But
Yes, sir.
here they
Uh,
have asked for stress ka. So
yes,
you
sir. For Tresca, we need to calculate sigma 1.
yeah sigma one minus sigma three. So that's
Yes.
why I calculated a sigma one, sigma two, and sigma three for one mysis as well. So also you can
Okay.
use that equation, that is sigma x minus sigma y square plus sigma y minus sigma z square plus sigma z minus
Sigma
sigma x
x, sigma x.
square plus 6 uh, tau xy square plus tau yz square plus tau zx square and
Yes.
square root of that equation. You can use that
Yes.
as well.
Yes. Actually, I calculate from this equation. I got the same value. That's
Yeah,
why I'm asking.
yeah, yeah, yeah. But in the
Okay.
Tresca, I need to find out the sigma 1 and sigma 3. So it will be the double calculation. So I avoided the double calculation. In the one go, I find out the value of sigma 1 and sigma 2 and sigma 3. And now I can just use the uh, separate equation for one mysis and Tresca, and I will get the answer. Okay, that equation also you can use. No, no issues. Yeah.
Sir,
Yeah.
actually, sir, is there no equation or no method for calculating the Tresca from the sigma x or sigma y? Means
Uh,
is it possible?
so yeah, if any of the like suppose sigma one and sigma three is there, na. So like here, okay. So here sigma x, tau xy, tau xz. So and tau yx, tau sorry sigma y, tau yz, tau zx, tau zy, and sigma z. So here, in only one case you can do. Here, it is sigma x is given and these two component are zero. Okay, that is if no shear stress is
Is
acting on that phase,
the
then
principal
that will
stress?
be our principal stresses. Similarly,
Yes.
here sigma z is given and no stresses are given, means shear stresses are there, then that will become our simply principal stress. So in that case only you can use directly.
Okay,
Otherwise,
sir.
you need to find out the sigma 1 and sigma 3.
Okay, sir.
Yeah. The third question is like that. A material is tested under the state of stress sigma 1 equal to 3 sigma 2 equal to minus 2 sigma 3. Yielding is observed at sigma 2 is equal to 140 MPa. What is the yield stress in simple tension? And if the material is used under the condition such that sigma 1 is equal to minus sigma 3, sigma 2 equal to 0, at what value of sigma 3 will yielding occur? Assume distortion energy criteria of yielding. So distortion energy is also known as
One
on
Mises.
my face. So now try to solve it. It's very easy question. It's just 2 minute question you can solve. Did you got the answer, Mr. Swastibrata? Is it
No,
Swastibrata or Swastibrata?
Swasti brother.
Okay,
So you can call me as Swasti.
okay, okay. So here, what they have given, let's write the given. They have given that sigma 2 is equal to 140 MPa. Sigma 1 is 3 sigma 2. Okay, that is 3 into 140. How much? 420 MPa. Now we have 3 sigma 2 is equal to minus 2 sigma 3. So sigma 3 is how much? Minus
Minus 210.
sigma 2. So minus 3 by 2 into 140. So how much? Minus
Minus 210.
210 MPa. Okay, so now I got the values of sigma 1, sigma 2 and sigma 3. So now what they are asking, the yield stress in simple tension. So when does yielding happen? According to von Mises criteria, when effective stress of one Mises is greater than yield strength, is it not?
Yes, sir.
Yeah. So for yielding should be happen, the sigma V should be greater than yield strength. Okay. So now they are asking me for the yield stress. So what I will consider that sigma bar should be equal to yield strength. Then only if sigma bar V is greater than yield strength, only it will yield. And at sigma bar equal to ys, it will not yield. It will be the yield strength of the material. So I have the equation sigma bar is equal to 1 by root 2 sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 whole square. So now if I put the value, sigma 1 is how much? 420 minus 140 whole square plus sigma 2 is 140 minus of minus 210 square plus sigma 3 is minus 210 minus 140 whole square. So 1 by root 2 sigma bar V. 420 minus 140 is how much? 280. 280 square plus 350 square plus minus 350 square. So how much it is coming? Sigma bar V. Mr. Swatibrata, how much it is? Mr. Swasti,
The 546.71.
546.71 MPa. So as this is the effective stress, it should be equal to our yield strength. Then only, if effective stress is greater than this value, then only yielding should happen, because we are considering it as the yield strength. So now, if what the second condition they have given, like if the material is used under conditions such that sigma 1 is equal to minus sigma 3, sigma 2 equal to 0, at what value of sigma 3 will yielding occur? So, so they are saying, let's assume this is the yield strength of the material. So what is the minimum value of sigma 3 that is needed for the yield, for yielding to be occur? So what they are saying, for part 2, sigma 1 equal to minus sigma 3 and sigma 2 equal to 0 at what value of sigma 3 yielding will occur. This is what they are saying. So can you find out, Mr. Swasti? So we have the equation sigma bar V, the same equation, that is 1 by root 2 sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. So in this, what they are saying, sigma 2 is 0. So this term 0, this term 0. So now we left with sigma bar 1 by root 2 under root sigma 1 square plus minus sigma 3 square plus sigma 3 minus sigma 1 square. Okay. We have the value of sigma V bar, this value. And here we have the equation. So you can get the easily value of sigma 3. So tell me the value of sigma 3. So this is 546 1 by root 2 under root. Sigma 1 is minus sigma 3, means sigma 3 square plus sigma 3 square plus here sigma 3 is given and sigma 1 is minus sigma 3. So 2 sigma 3 square. So 546.71 is equal to 1 by root 2. So 6 sigma 3 square, that is root 2 into 546.71 divided by root 6 is equal to sigma 3. So what is the value of sigma 3? So sigma 3 is how much?
So actually, I got 2.34.
How did so? Root 2 into 546.71 to the power under root 6. I think you are making mistake somewhere. So sigma 3 should be around 315.2 megapascal. So if sigma 3 is greater than 31.65 megapascal, then only yielding will happen. If it is less than 315.65, then yielding will happen or not?
No, sir.
No, yeah. So this was the question. So here the third question is given. A region on the surface of a 6061T4 aluminum alloy component has strain gauges attached, which indicates the following stresses: sigma 11 70 MPa, sigma 22 120 MPa, sigma 12 60 MPa. Determine the yielding for both the Tresca and von Mises criteria given that sigma naught is equal to 150 MPa. So here I can write sigma 11, sigma 12, sigma 13, sigma 21, sigma 22, sigma 23, sigma 31, sigma 32, sigma 33. Okay, I can write stress tensor like this. We have seen we can use numbers as well in the very beginning. So if I put this value, so how it will look like: 70, 60, 0, 60, 120, 0, 0, 0, 0. Is it not? Are you getting my point, Mr. Swasti?
Yes, sir.
Now try to solve like yielding for the both stress and von Mises. It's very simple. And tell whether yielding will happen or not.
So von Mises is 130.192.
Oh, how much? 139.192. And Tresca?
So yes, sir. Tresca is
Sigma 1 minus sigma 3. Sigma 3 is 0. Means sigma 1. What will be the value of sigma 1? That
just 70.
huh?
Sigma 1 is 70.
No. You are getting wrong. So let me solve. So here I need to find out sigma 1, sigma 2, and sigma 3. So I can use equation sigma p cube minus I1 sigma p square minus I2 sigma p minus I3 equal to 0. As this is the case of plane stress, this is 0. So sigma 3 and tau xz and tau zx and tau yz and tau zy equal to 0, I3 becomes 0. Is it not? So I1 is equal to sigma x plus sigma y plus sigma z. Sigma z is 0. Sigma x plus sigma y, 70 plus 120. It is 190. I2. I2 is how much? Tau xy square plus tau yz square plus tau zx square minus sigma x sigma y minus sigma y sigma z minus sigma z sigma x. Here this term 0, this term 0. Tau zx is 0, this term 0. Tau yz is 0. So only tau xy. So I2 is tau xy is how much? 60 square minus sigma x and sigma y. What is 70 into 120? So how much it is? It comes out to minus 4800. Is it not? Are you getting the same value, Mr. Swatibrata?
Yes, I'm doing so.
Yeah. Now, if I put sigma p cube minus 190 sigma p square minus plus 4800 sigma p plus 0 equal to 0. So I will get sigma p minus 190 sigma p plus 4800 equal to 0. Now this is just simple quadratic equation. You can solve and you will get a root like sigma 1 equal to sigma 2 equal to sigma 3 equal to. Tell me the roots. So sigma 1 will be 160 MPa, sigma 2 will be 30 MPa and sigma 3 will be 0 MPa. Okay. Now, according to von Mises, sigma bar V is equal to 1 upon root 2 under root sigma 1 minus sigma 2 square means 160 minus 30 square plus sigma 2 minus sigma 3 is 30 minus 0 square and plus sigma 3 minus sigma 1 0 minus 160 square. So sigma bar V will be 1 upon root 2 under root 160 minus 30 130 square plus 30 square plus 160 square. So sigma bar V will be how much? So how much sigma bar V is coming? So it is coming out to be 147.31 MPa. So sigma bar V is less than sigma naught, that is 150 MPa. So whether yielding will happen or not? So no yielding. Are you getting my point, Mr. Swasti?
Yes, sir.
Yeah. Now for trace ka sigma 1 minus sigma 3. Sigma 3 is 0. So sigma bar T is sigma 1. Sigma bar T, sigma 1 is 160. So sigma bar T is greater than sigma naught. So what will happen?
So your yielding occurs.
Yielding will occur.
Sir, for the trace ka,
Yeah.
means as the given question here, sigma 3 is already 0,
Yeah.
sigma 3 3. So we can easily find out the sigma 1, sigma 2 or sigma 3 from the principal stress equation.
Yeah.
So means can we do that?
Yeah, you can do that.
Okay, okay, sir.
So this was all about our uh, what I can say, the week 4. Okay, so we have discussed the week 4 content. So and yesterday session we have discussed the assignment as well. So if you need to want to discuss the solution of assignment, you can visit yesterday's lecture, so you will get a better idea. So for now we will end our session here. If you have any doubts, you can ask, or we will meet in the next session.